Higher order functions are functions that either take one or more other functions as parameters or return another function when called themselves. Easy, right? But, and hear me out, what's a function? On Theo's Quest, we usually talk about data and types. But functions aren't data, they're just a set of instructions, so how can we pass them around? And while types can be involved in defining functions, are functions themselves typed? Kinda. Functions aren't data, but they do exist as a set of instructions in memory when your program runs. And if it's in memory, that means it has an address, and if it has an address, we can create a pointer to it. Fun fact, unlike raw pointers, function pointers are safe in Rust. But in Rust, pointers are typed, so what does a function pointer type look like? Functions have signatures. In this function, we have two parameters, a string slice and a U8. The return parameter is a string. The type of a function pointer is actually just this information written like this. This is basically the function signature written without any names. We can set a variable of that type to point at our function, though we wouldn't normally do this in line because Rust can infer the type of the function pointer. Where this is actually useful is when defining another function that takes a function this shape as a parameter. Using the repeat function type alias here makes the function header a lot easier to read, and if we need to, allows us to reuse the alias in multiple places. Referencing a function using a function pointer can be especially useful for things like filters, maps, or folds. In this example, we have a range of numbers 1 to 10. We use regular functions to filter out odd numbers, map each number to a string, and then combine what is now an iterator of strings into a single string. It's worth noting though that isEven has the quirk of needing to explicitly take a reference to a usize because filter gives us a reference to t even if t is copy. We can also return function pointers from other functions. Here we have two functions that take a reference to a usize and return a bool, a type alias that matches those function signatures, and a function that returns a pointer to one of the other two functions when called. We can call createEvenFilter to get a pointer to one of those two functions. But I think at this point we have to stop and wonder, how useful is this really? We can defer the choice of what code to execute until runtime, but you can literally do that with if statements and other branches. Using function pointers could be a little bit tidier depending on the circumstances, but honestly, most of the time you probably won't use them in higher order functions all that often. Higher order functions are more useful and frankly more interesting when you can configure the functions you send them at runtime, but you can't really do that with function pointers. Functions are simply a set of instructions. If we want to configure how they behave later, we need to apply a little sprinkle of data. We can provide functions with a scope that contains some data, and then pass around that bundle of instructions and data. This is where closures come in. Rust has 3 types of closure. Well, 6 technically, but we'll talk about the Beardo weirdos from the Mirrorverse later. I'll give you a few seconds to think about why Rust specifically needs 3 closure types when you bring stored data into the mix. Let's take a look at a very simple example. We'll create a string, then we'll create a closure. Closures look a little different from functions. They aren't named, but they can be stored in variables. They use pipes to surround parameters and are followed by an expression which is run when the closure is called. For clarity, we're going to go through 3 closure examples, and each one is going to store data in a variable called response before returning it. This isn't necessary. It's more verbose than we really need. I just want to make it consistent and clear. This closure references the greeting. The reference to that string will be bundled into the closure. Because of this, behind the scenes, Rust will make sure that the closure doesn't outlive the thing it's referencing. When we run the closure, it gives us back a string using the reference to our greeting and the provided name. Running it again with a different name gives us a different string. Greeting is still available and hasn't changed. We can also create closures that modify the data they're given. In this version, we need to make sure the data we're referencing, greeting, and the closure itself are marked as mutable. This may initially seem odd, but there are 2 things to bear in mind. First, conceptually, calling the closure multiple times will produce different results as if we're modifying the closure itself. Second, technically we are modifying the closure itself. The closure is storing a mutable reference to some data, so just like almost any other data type that wants to let you mutate something it's holding, it too must be marked as mutable. This closure will capture a mutable reference to greeting. We didn't need to tell it to do that though. Rust knows that the pushStruct method on strings requires a mutable reference, so that's what it stores. Again, it's a workout if we're using this safely without us needing to do much at all. The first time we call this closure, we'll get the same result the previous closure gave us when called with the same name. But the second time we call the closure, we get a difference. This is because we mutated the greeting string, which we can see if we inspect it. Finally, we can actually just give the closure ownership of the data being used. In this example, I'm using the add trait to combine a string with string slice references. Don't do this. For types that aren't copy and string is not copy, add consumes the data, meaning after we call this closure, we can never call it again. Luckily, Rust knows this and will prevent us compiling code that attempts to do so. If we uncomment either of these lines, we get a borrowed after move error. Earlier, I mentioned that Rust has 3 basic types of closure. Did you spot them? Just like anything to do with data, Rust has 3 ways to think about it: immutably referenced, mutably referenced, and owned. In reverse order, our final function took ownership of the data and therefore could only be run a single time. This type of closure is known by the trait fn_once. Our middle closure captured a mutable reference to the data and therefore could be run as many times as we liked. This type of closure is known by the trait fn_mute. Anything that implements fn_mute also implements fn_once. Our first example only captured an immutable reference. This type of closure is known by the trait fn. Anything that implements fn also implements fn_mute and therefore fn_once. And if you're wondering, function pointers which do not capture any state implement all 3 traits. This is why we could use function pointers in filter, map, and fold earlier, which accept anything of type fn_mute. If we go back to that example, we could use closures instead. If your closure is very simple, like these, this may be preferable to writing a named function somewhere else. Finally, to round things out, a closure that doesn't capture any state is treated as if it's a function pointer by Rust. Now, why was I just drawing a load of weird circles? This is my mental model for working out when to use which closure, not just for writing closures, but for consuming them too. You can imagine these types as being blocks that fit into slots. When you're writing something that consumes closures, you want to use the largest possible slot that allows the most number of blocks to fit. If you're only going to run the closure once, you can accept fn_once and you'll be able to take any kind of closure or function pointer. Often you will need to run a closure multiple times though, in which case fn_mute is the next best option, but you won't be able to accept fn_once closures. If you're writing a closure that needs to be passed to something else, then using the smallest possible block will make your closure more portable. If it doesn't need state, then a function pointer or stateless closure will give you the most flexibility. So those weirdo mirrorverse closures. Async closures are relatively new, and so you'll see a mixture of ways to encapsulate features in closures. More recently, async fn, async mute, and async_once was stabilized, allowing you to write async in front of a closure. Because this is a relatively new feature, in older code you'll likely see closures with async blocks, which feels backwards, but makes sense. The async keyword, whether applied to a function, code block, or now a closure, is syntactic sugar that allows 2 things. First of all, the ability to await a future. And second, and more importantly to what's happening here, it says, this thing produces a future. If you create a standard closure and immediately return an async block, then you are returning a future from that closure. So in a way, Rust has had async closures for a while, but in a way, it also hasn't. Using this older method causes all sorts of problems with lifetimes, which leads to some really fiddly management of references and ownership. One day, Rust may introduce even more closure types. One that I'm personally excited by is that Rust contributors have been thinking how to add generator functions, which implies both generator closures and async generator closures. Closures and higher order functions are conceptually complex, but as we start writing them, they're really clean and incredibly powerful. In Rust specifically, the lifetime juggle can make things a bit more complex and can be a bit of a headache to work around. Been there, believe me. However, we can see that the amazing people contributing to the Rust language continue to improve usability and ergonomics. Just a reminder, if you enjoyed this video, don't forget to hit the like button, and letting people know about the channel is the best way to support it. Next time, now we've seen how functions can be passed to other functions, we're going to get a little wild. Our next video is going to explain monads. Don't worry though. The pattern itself is actually super cool and much easier than it sounds. I'm going to explain the pattern while avoiding the complex language surrounding it. This will undoubtedly frustrate the purists, but it's such an awesome pattern it's worth discussing anyway. Hope to see you then.